Welcome in this finite volume series. Right now our discussion is on convection diffusion system, and where we have stopped so far, we started with a one dimensional system and we looked at the discretized equation for a convection diffusion system, and what we have looked at is that the central difference scheme and the upwind scheme, and also we have compared their accuracy for the against the analytical solution. So, if you recall from the last lecture, this is where we stopped and we have seen this particular figure which shows the profile of the scalar against the varying Peclet number, and we have seen that at the some region which is for low Peclet number region, all the numerical scheme like the upwind scheme or the central difference scheme, they show or exhibit proper behavior or exact behavior while comparing against the exact solution or the analytical solution, but both of them start differing as they move outward. That means this direction and this direction for high Peclet number regime, and CD, that the central difference scheme, shows the completely different behavior, while the upwind scheme shows the behavior. It follows proper trend, but still there are certain discrepancy. Now, the point was that there are one has to make some trade off between these two. One is that because the central scheme is higher order accurate, upwind scheme is lower order accurate, but at the same time upwind scheme is much more stable, central scheme is not stable for the kind of system when the convection is dominated. So, with that note, now we will start looking at the scheme called the reverse upwind or downwind scheme. This is essentially, one can think about it is a reverse upwind scheme, and we consider this particular stencil as we have done. So, this is our point of interest, that particular element number C, and we have E, W and the fluxes at the faces. This is the west face, this is east face of the element. So, primary concern is that how do we or how one evaluates the fluxes at the faces. So, for example, at face E, if you look at it, then phi E or phi E is going to be phi E if m dot E greater than 0. So, it is a reverse upwind scheme, while compared with the upwind, if the east face mass flux is greater than 0 or positive, then the phi E was supposed to get the contribution from phi C. Now, the other case, if m dot E less than 0, this will be phi C. So, in the reverse upwind, it just become flipped. In the conventional upwind scheme, what was there? If the mass flow rate is greater than 0, the phase value is assigned to phi C, and if mass flow rate is less than 0, phase value is assigned to E. Now, similarly, at phase W, phi W equals to, if m dot W greater than 0, it is phi W, if m dot W less than 0, it is assigned to phi C. So, again this is flipped as compared to the conventional upwind scheme. Now, one can write the advection fluxes. If I write the advection fluxes, then one has to get m dot E phi E, which is nothing but modulus of minus m dot E 0. So, the maximum of that into phi C plus m dot E 0 phi E. So, that will get me back the flux C E convection phi C plus flux F E C phi E plus flux V E, which is again for convection. Similarly, at the west face one can find out m dot W phi W, which is nothing but minus m dot W 0 phi C plus m dot W 0 phi W. Then we get essentially flux C W convection phi C plus flux F W C phi W plus flux V W convection. So, now if you put everything back in the discretized equation, the equation will look now flux C plus flux C diffusion plus C W convection plus flux C W diffusion multiplied with phi C plus flux F E convection plus F E diffusion phi E plus flux F W convection plus diffusion phi W equals to 0. So, that becomes the equation for the discretized system, and if you put them in a more compact form, so this would look like A C phi C plus A E phi E plus A W phi W equals to 0. So, the discretized equation look similar. Now, once you get that, the coefficients are going to be different compared to conventional fluxes. Here A E is flux F E convection flux F E diffusion, which is m dot E 0 minus gamma E A C by del x E. For E W, this is flux F W convection plus flux F W diffusion, which is m W 0 minus gamma W S W by del x W. And AC is summation over phases flux CF convection plus flux CF diffusion, which is minus m dot E 0 plus gamma E minus m dot w 0 minus gamma w S w del x w, which is, once you put them together, it is A e plus A w plus m dot e plus m dot w. For continuity, this would be 0. So, AC becomes like that, and BC is minus F flux VF convection plus VF diffusion, which is nothing but 0 in this case. So, now what one can do, you invoke the continuity equation. So, invoke continuity equation and assume uniform grid, diffusion coefficient gamma is constant, then the value of phi c minus phi w divided by phi e minus phi w equals to 2 minus Peclet number 4 minus Peclet number which will essentially boils down to 2 minus 0 divided by 4 minus Peclet number. Now, if you plot this equation, it is quite obvious. If Peclet number goes to 4, this denominator becomes 0 and the whole solution become unbounded. So, the downward scheme may be beneficial when blended with other scheme to predict some sharp interfaces. However, its introduction here will be discussed more details in the subsequent analysis. So, what we have looked at is that schemes like central difference scheme, upwind scheme, downwind scheme, downwind difference scheme, like that. Now, the thing which are all applicable to all of these scheme are the truncation error. So, this is one thing which is inherently come to this kind of discretization or numerical discretization. So, this truncation error lead to some sort of an numerical diffusion. So, once there is a numerical diffusion, one has to take care in such a way that some anti-diffusion also be there to handle this kind of a diffusion. So, the numerical diffusion actually takes away the solution from the exact solution. Now, we will look at again from scheme wise what are the error and what are the issues associated with it. So, to start with, we will start with the upwind scheme. So, the upwind scheme, let us say the flow is in the positive x direction. So, that is the convention that we take into account. So, which will result that phi e equals to the phase phi c and phi w would be phi w. Now, the convection diffusion equation system which was discretized is that rho u delta y e phi c minus rho u delta y w phi w minus gamma d phi by dx delta y at east phase minus gamma d phi by dx delta y w equals to 0. Now, we go back to our standard Taylor series expansion. So, then what using the value of the flux we calculate. So, we start with the cell and using the value of the phases that we use to calculate that. So, phi e plus d phi by dx at e x c minus x c plus half d 2 phi by dx 2 which is x c minus x c square and so on. What is there is phi e minus d phi by dx e x c minus x c plus so on. Now, if you have uniform grid, then you can phi c equals to phi e minus d phi by dx e del x e by 2 plus half d 2 phi by dx 2 at east del x e by 2 square. Similarly, the phi w can be written as phi w minus d phi by dx w del x w by 2 plus half d 2 phi by del x 2 at w 2 square and so on. Now, we are removing the higher order terms. Now, once you use this expression in the equation of this one. So, the resulting equation becomes the left hand side which was there, it is rho u delta y and e phi e minus d phi by dx e del x by 2 minus rho u delta y w phi w minus d phi by dx w del x w by 2. So, that is the first two term or the convective flux terms can be expanded like that. So, once we do that, and obviously we can retain the diffusion component as it is. So, these components we can retain J E D and J W D. So, those are the diffusion component. So, they will remain as it is, and now if you rearrange the terms, what it would become is that rho u del y E phi c minus rho u del y w phi w minus gamma d phi by dx del y east minus gamma d phi by dx del y west, which will essentially become rho u del y e phi e minus rho u del y west phi w minus gamma plus rho u del x by 2 at east face d phi by dx delta y at east face minus gamma plus rho u del x by 2 at west face d phi by dx delta y w. Now, so it is now very clear that the discretized equation which is solved. So, this is the equation that is now being solved. So, this is now being solved. Now, in this solved equation we have an added component like this much at the east face and this much at the west face. So, which is essentially act like a numerical diffusion. So, that is there rho u del x by 2. So, that is the sort of one can think about the truncation error which is knowing there. So, this numerical diffusion actually it reduces the accuracy of the solution. So, this is the one which actually diffuses the solution more. So, therefore, the convection diffusion equation has an effective modified value of the diffusion effect. So, not only this gamma d phi by dx, that is the term, we get an extra term in the context of discretization and which is sort of known as numerical diffusion, and that has impact, but at the same time this has some negative impact on the solution because the accuracy actually degrades, but at the same time this also some kind of provides or ensure some level of stability. So, that is another issue. It actually make the system quite bit stable because of this diffusion, and make sure that the solution remains bit bounded and physical. Now, another important thing is that theoretically the contribution from this term, the numerical diffusion term, should be less, and that is exactly what happens when you move down to higher order scheme and you try to reduce the impact or effect of this numerical diffusion. Now, we will look at the second case is the downwind scheme. So, in the downwind scheme, since it is the reverse upwind scheme, your phi e is now phi e and phi w is phi c. So, the discretized equation is rho u del u phi e minus rho u del y w phi c minus gamma d phi by dx delta y east minus gamma d phi by dx delta y west, which is 0. That is our discretized equation. And once we have that discretized equation, again assuming the uniform grid 1D, we use the Taylor series. And what does that do? Phi e equals to phi e plus d phi by dx at e del x e plus e square by 4, like that, and phi c is phi w plus d phi by dx w del x w by 2 plus half d 2 phi by dx 2 w del x w by 2 whole square. And you can leave out the higher order term and you take everything back and put in the, so you use this information and put it back in the discretized equations, and once we put it back in the discretized equation, the resultant equation looks like rho u del y e phi e minus rho u del y west phi w minus gamma minus rho u del x by 2 at east face del phi by del x delta y east face minus gamma rho u del x by 2 w d phi by dx delta y w. Again here the numerical diffusion is of the order of minus rho u del x by 2. So, that is the term. Now, here compared to the standard upwind scheme, if one see the numerical diffusion comes with a negative sign, which acts as in decreasing the diffusion coefficient. So, and its effect is so called, this will like an anti diffusion. So, this case downwind scheme, this is termed as a anti diffusion because the error comes with a negative sign. Now, the predictions which are obtained using the downwind scheme are found to cause clipping of advected profiles. In fact, solution to the 1D convection diffusion equation which are obtained using this particular scheme can be more oscillatory compared to that of a CD scheme. So, we will stop here today and we will take from here in the follow up lectures. Thank you.